All right. So everybody's got, we're going to play with this first. We're going to try and do this without breaking any of them, but you know, whatever, it's science, we can break shit.
Yeah.
It's not people. It's not people. So what you're going to do, no. I don't believe in safety. I believe in danger. So we shoot guns between sets of squats at my house. Yep, everybody needs one of these. So your design's a little bit different than mine. I had to tie mine like this because I drilled the holes too big and I couldn't just put a knot in it and have it hold. So here's what I want you guys to construct. You need to tie your knots. You may have to move the knots in your rope, but you need to have a little tension on it before you start turning the turnbuckle. The way this turnbuckle works is if you get somebody to hold each end, turning the turnbuckle in one direction, one of these screws is left-hand threaded, one is right-hand threaded, it'll pull them closer together. Turning it in the other direction will loosen them. So open them all the way up and then tie off your knots so that you're in about this configuration right here. And if anybody's ever worked with a bow and arrow before, you know how to do this. You just get your knee in here and boom, and you can take it apart and put it together. So you're going to have to play around with your knots a little bit. You're going to have to move them. Tighter is better than looser for this. Yeah, that's true. It might be easier just to pull on one end since you guys are just knotted at each end. It might just be better to pull a little rope through and tie a new knot in the end. Oh, we've already broke one. Oh, look, we have a spare. So just so you guys can see here, let me take this one apart real quick. This is kind of about the gap you need with the turnbuckle fully extended. You kind of need about an inch, inch and a half gap. Yeah. No, it can be one end or the other, it doesn't matter. How's it going over here?
Good.
Keep going.
Oh, that's all the way?
Keep going. It's all
All the way down. Yeah, wait until something breaks. No, mustard's already broken.
No.
we did.
Fuck it. All right, so how's everybody doing? You got it? Almost there? Oh yeah, that's good, Alex. So you got plenty of room to play. You can go, just keep tightening that down, that thing almost breaks. You'll hear it crackle. Okay, so what I want you guys to do now is, and we'll go get some like 2.5 pound plates or something and just put some weight on them and see what happens. And then we're going to take them back apart, put the same weight on them. We'll put our sticks in first. We'll have to find a way to raise it up a little bit, maybe put some plates on the platform. And we'll observe some things about what happens to deflection now that we have some tension added to the equation. So if you're really tight like these guys are, now you're going to have to hold the ends so they don't tilt over and all that kind of stuff. But this is just, you know, really cheap budget kind of stuff. And you can almost notice right away that than just the board itself, this structure is a lot more rigid. But you can also see the ends are still trying to get farther apart and are stretching the rope. right? So what do? Well, we get more tension. And one of the things they do in buildings is they take a king post, put it in between the rope and the beam, and now you've added more tension to the structure. Now it's not going to work really well here because we're going to hit the floor, but you can see now we've pre-stressed the wood more, right? But we've also tensioned the rope more. Can anybody tell me what force is in this member now? Compression, yeah. And the reason I put this here is so you guys can, if you don't understand that, just stick your finger in there and then tell me what force you have in there. You'll understand instantly. And of course, everybody who's been outdoors also knows what the other thing I've constructed is, which is my, gotcha, success. It's my bow and arrow. So, this just gives you an example. Bows, bridges, arch bridge, bow and arrow. A lot of these things come from examination of one problem and then converting it for use in another. If I take a bow and instead of shooting an arrow from it, I block the bow, open with the arrow, it makes it harder for these ends to go apart from each other. What can I make out of this? I can make roof beams out of this, out of a lot of really lightweight components instead of a big, huge post of a tree, which, if you got to carry something up 3 stories, you'd rather carry this or a tree. It also conserves material when you're building. What if you don't live right next to the forest? Yeah, you live right in the forest, okay, you got trees all around, but what if you live out in the plains? You got to bring all the material to where you build. So a lot of these engineering solutions were for reasons like that. Scarcity of material, pain in the butt of building what they were wanting to build, but also for lighter materials being able to make stronger structures. Or kill your neighbor. Bang, hey, we're going to go kill my neighbor using my roof beam. So, and ironically enough, this is about the height of an English longbow right here. So yeah, so that's the whole purpose of doing this. Now, so especially you guys right here who've built a really nice arch, tighten that up even more. Keep tightening it up until, like it says uncle. Here, I'll make your life easier. You ready? Here, tighten it now. Oh, we're going to town now. You've discovered whoa? Oh, yeah. All right, let's take a look at that. Oh, look at that. Much more of an arch now. Now what happens? Hold the beam so it doesn't tilt. Let's just watch what happens. Even less deflection, right? All right, cool. More tension means less deflection. All right. All right, so now let's go ahead and recreate that last drawing that I had up there. And the way we're going to do it is, you guys are going to take this. Now, this is not unobtainium. This has mass, right? And weight. And what that means is there's a centroid to this beam. It's like the center of mass. It's our fancy name for center of mass. So what we're going to do is we're going to take this and we're going to flip this through one of these holes in the rack right here. And you guys are going to do this as like a team building exercise because doing it by yourself is hard. But we're going to create this. And then we're going to start making observations. And the observations that we're going to make are, notice that I'm holding the beam right here. Why am I doing that? I'm not fixed to the rack here, right? There's nothing supporting this end. And there's friction here, but there's not enough compressive force to make that friction mean anything yet. But what I want you guys to do is just kind of come to an understanding that how much harder you have to pull on this rope to do that. And it's going to move around a little, so I suggest you have one teammate here to just kind of make sure that it doesn't move very much. And you can play around with it by trying to pull this away from the rack now and see just how much compressive force is there, as opposed to down here where really not much compressive force, right? And then, since there's 5 of you to a team, grab some weight, and I've got some ropes over there that I'll bring you by. Run a rope through here and just hang a weight from the end and observe what happens to the tension on the rope or the pain in your hand that you're pulling on the rope with. And I just want you guys to have a feel of this sort of thing, because we'll go back and talk about this in relation to the human anatomy when we go back to the whiteboard in another 5 or 10 minutes, okay? Let's go.
More or less?
And really what I want you guys to do is just take a turn pulling on that. Don't pull it off. You're cheating. Closer it gets to the 2x4. While you're doing that. Yeah, I'm stalling. All right, so everybody come on over here and gather around over here. What we're going to do now is start piling some weight on this. But first, we're going to measure how much have we got to the ground, to the top of the bridge deck. And the center is right here at these marks, and I'm just going to say it's 33 inches. So we're going to start piling some weight on here. And if one of you guys can just steady it there, because this is not a great platform, I promise you won't get hurt too bad when this snaps.
I'm generally hurt anyway, so.
I don't know, this may snap at any minute. I have no idea. You know, I mean, you got Sully right there. If I get hurt, you know. He can do New York CPR. You know what New York CPR is, right?
It's like you're gonna die.
Get up or you're gonna fucking die. So how much we got on here so far? 50? 60? Anybody want to take a pool? 70? $80. This is getting intense.
So you guys on the abutment might want to like turn your faces away.
Yeah, because cables are really bad.
Just saying.
So let's just go with 10, 20, 30, 40, 50, 60, 70, 80, 90. How much is it deflected, you guys think? 1 inch? How about 1 3/4 inches? Pretty good. Not much deflection. All right, flip it over. Yeah, just, oh, yeah, sunglasses are in the danger zone here.
Oh, 1 second.
All right, and same side back up. That way, we're not, we may have pre-bowed it the other way, so I don't want that to influence our experiment too much. But now, we've got 16 3/4. inches. Oh, your bridge is in the water. So just a really, really clear example of the power of a tension compression structure. 13 and 3/4 of inches deflection versus 1 3/4 for the cost of a couple of holes and a little bit of cable. Let's start here at the femur. I'm just going to draw it there because it looks good there. It may not be anatomically right, but whatever. Is Patrizio still here? Oh, good. So he can't criticize me this year. Excellent. I like that. And we're going to say the end of the femur is somewhere around here. We have a patella here-ish. Actually, it's more down about here-ish. And then for purposes of our discussion, femur, tib, fib result is one line. That's all we're going to look at right now, other than we're going to draw in the lower section of the back. And we're going to draw it in as rigid because everybody is holding themselves in normal anatomical extension and just perfectly doing so. So here's the lower part of the back. What attaches here? Originates here? Hamstrings. And they insert, right? Quadriceps originate various points around here, right? Except for one, which crosses the joint. But we're going to ignore it right now for simplicity's sake. But we're going to say, for in sake of our argument, quadriceps attach here. Quadriceps tendon into the patella, and then patellar tendon to, I believe, roughly in the same area, same condyle as the, or same, help me with my words here. It inserts into the tibial plateau. Thank you, Tom. So these muscles groups are pulling on the same 2 points. How does that work? They're pulling on the same point. All right, so at the bottom of the squat, when everything has stopped, things are static. It means all of the forces are in balance, right? Nothing's moving. What force do muscles exert? Canadians, what force do muscles exert? Tension, right? So you have the quadriceps group pulling on their origination on the femur. They become tendinous and encapsulate the patella. And then insert into the tibial plateau. Remember what we talked about? We talked about that, right? This results in what in the hoop? It results in tension. Here's a hoop. Now, if these 2 points are trying to get closer together, what's preventing them from doing so? They're attachments, but also basically what sits between here and here, and what sits between here, and these just going like this is the femur. It's the only thing that's there. And if this rough area is trying to go this way, and this area is trying to go this way, what does that mean the femur's in? Compression. And only compression. There's a little bit of bending there. There's a little bit of bending because at the bottom of the squat, some of you folks who are like me collide a little bit down there and load up the tops of your femur with a load like this. But there's nothing really applying that load there. Now, for purposes of illustration of moment and torque in the knee and the hip, we show the force application of the weight and where it is. But that's not the same as actually sitting the weight in the bar on your femur at that point. It's kind of the same. It gets really complicated. It's kind of the same. But it's different. And it's different because you have a bar here. You have this segment length here. This bar is being pulled towards Mother Earth by gravity in that direction. That causes a rotation around this joint of that. Note that there's not any moment in this joint because that joint in and of itself has no friction or any other mechanism to provide moment force. It's just the pivot. It's the center of the seesaw, and that's it. What is preventing this rotation is this group of muscles, which is causing a counter rotation equal and opposite to the force of the bar. That results in tension in the hamstrings. Now, tension in the hamstrings is going to try and shoot the femur in that direction. But it's not going anywhere, is it? Because it's restrained by the patella and the quadriceps and patellar tendons from going anywhere. That's why the patella is so important, especially in animals like us that squat down, because it is the main piece of anatomy that prevents your femur from going anywhere in that position. And like we talked about before, force going this way creates tension in that structure, right? Well, what resists that tension? The only thing that can is quadriceps contraction. It's why no matter what kind of squat you do, it works your quads. Imagine, as a thought exercise, what would happen at the bottom of a squat if somebody just came up, took a nice big knife and went right across your quads. What would happen to your knees? So, now we've taken some very basic concepts that we've had, that we played with over here, especially when you took that 2x4 and jacked it all the way up really, really close to the rope, and we're pulling on it as hard as you could. Think about that. Your angle of attack on that 2x4 now is not so good anymore for resisting vertical force, and so it takes a huge amount of tension to hold the end of that beam up. And that will give you some idea of, because of the low angle of attack all of these muscles have, just how absolutely incredibly strong they are. 405 on the bar is impressive. I'd really like to get with Sully and Jordan and get some DEXA scans of some quadricep cross-sectional area and hamstring cross-sectional area, and then measure, you know, joint to sit bone distance, and figure out just how much tensile force per square inch is in the muscles. It is some astronomically high number, and even higher than that is the compressive force in the femur. Using this same analysis, you can work your way the rest of the way down the leg. Right? Here's a segment length. Gravity's pushing this way. It's causing rotation around the ankle that way. What resists rotation around the ankle that way? Calves, right? Gastroc muscles. So these muscles here, which wrap under the heel and attach in various places down here, are providing the counterforce to that rotation. You can do this analysis at each of the joints, like this. And what's really cool is if you go hunting around the internet, you can find guys who've already done it. Oh, I forgot all my drawing. We can look at rough hip joint position, bar location, horizontal segment around the hip and around the knee, and start calculating torque at each of those joints for 100 kilograms on this person. If these drawings are accurate, torque around the hip here is 13.7 Newton meters. In a high bar squat, it's 15.9 Newton meters. In a low bar squat, 17.3. Much higher, which is what we've been saying all along, right? So when you guys all see weightlifting, this is what I see, is all of this stuff. Why is the human body doing what it's doing the way it's doing it? And so hopefully in my little discussion, which somehow got done in 1 hour and 15 minutes, I have no idea how I did that, I provided you guys just a little bit of insight into what's happening in the anatomy. We can certainly get a lot more complicated. Eventually we will. But for right now, it's just a very, very basic 2D, you know, not 3D, but 2D planar look from a side view of what's going on. Gets a little bit more complicated when you add a third dimension, say start looking at it from above, but a lot of the same principles still apply. Although when you start looking at it from above, that's when we have to start talking about that torsion that I was talking about, torsional shear in the femur at that point, because you have a hip joint and you have a knee that's outside, laterally outside the hip joint. And a line directly between them, that the only force resisting at that point is torsion, that segment length, when you spread your knees out. And there's some anatomical evidence of that that Jordan pointed out to me before my last talk, but it's a little bit complicated for today, and we're at about the end of my time. So now, questions about anything we did today? Or questions about any of this? This can be done actually, you can do this photographically, and you can do this really, really accurately, as long as you draw the vector for your weight and the angles the same way each time. In other words, the same anatomical landmarks each time. So if you're going to do this one of your trainees, you might want to have them dress in like a pair of spandex shorts so you can see where the landmarks are on his hip and things like that. Take a picture and start sketching on it. This is just basic geometry. You've got 100 kilograms, 9.8 newtons, that's acceleration due to gravity. 3 centimeters is the actual horizontal segment length here. Oh no, I'm sorry, I see what he did. He measured the actual segment length on the back, cosine 54 degrees, he measured the angle that it's at. You can see down here, cosine 54 degrees is the horizontal distance. So you now know 100 newtons and the horizontal distance. And for your trainee, you can look at how much torque is being applied at the knee and the hip, if you take a really good photograph from the side. Cool. Yeah, if you think of if you think of the bow actually that we made in the opposite, pulled in the opposite direction than we pulled it at, and you think of the wood as your spine, hips, femurs, and shank, and you think of the bow, the rope material as abdomen and quads, then when you push your hips forward, it starts to stretch those. This has got a lot of tension in it now. And then when it springs back, that releases a lot of tension into your anatomical structure. That's where that energy is coming from. All right. That's all for today.